Thanks for joining me. I am notorious for walking around, but they blocked me behind a microphone. So if I do wander across the stage, somebody yell at me and tell me to get back to the microphone so everybody else can hear me. It's great for y'all to show up. I'm always shocked when anyone shows up to hear any of my statistics talks. I have 3 of them. One about basic statistics that we use in DevOps every day. This one that you're going to see today on lying with statistics, and then one on probability, which actually starts off with a small wager for 2 hands of randomly shuffled card decks. And if anybody can match me 52 cards for 52 cards, I will be glad to pay them $1,000, but you have to play 2 and it's double or nothing. Because the odds of doing that, by the way, are 52 factorial, and there are less atoms in the universe than that number. So the odds of it happening twice, unless you manage to stack the deck on me, are pretty rare. So with that, and by the way, if you haven't noticed, I am killing time while people wander in, trickle in over the period of time here. So I'm Dave McAllister. I work for a company called Nginx, which is actually owned by F5, but fortunately they leave me alone mostly. Nginx is one of the most widely used open source projects in the world. It's a web server, it's a load balancer, it's a cache server, it's a mail server. And basically, roughly 45% of all of the web traffic on any given day runs through Nginx. Now, the good thing is 2/3 of that is the open source side. And our open source is Apache. I actually take that back. For Nginx Open Source Core, it's MIT, or BSD2. It's one of those. We just recently celebrated our 20th anniversary for Nginx, and we've got lots of other projects that go there. Along the lines of this, we will make a commitment that if we have open source code, the license will never change. We will never remove features from our open source code to put them into proprietary, and we will continue to innovate and drive forward all of our open source projects, of which currently there are 133. And most of y'all know about one. So get a chance, let's go that. So with this, subtle science of art, or basically, how are we going to lie with statistics? And it really kind of starts off with this. Way back in the dark ages, lies, damn lies, and statistics. And most people actually say that Benjamin Disraeli is the person who said that. However, to start off our lying point, Benjamin Disraeli never said this. It actually only shows up in the autobiography of Mark Twain, in which he says, "Figures often beguile me, particularly when I have the arranging of them myself, in which case the remark attributed to Disraeli would often apply with justice and force. There are 3 kinds of lies: lies, damn lies, and statistics." So statistics has been around. The farthest back we can track this type of lies, damn lies, and statistics goes back into a writing in the 1500s. So it's there. Now, that's not to say that statistics are bad. We use them all the time. We have evidence-based things. We use them to see how we're operating against our principles. We're looking at a cultural impact, how things change in those. We look at it as risk management. But you need to consider the source of the data that's inside of that. And you need to be able to have a healthy skepticism, because it's really just a game. We have people that misinterpret data. We have people who cherry pick it. We'll get into correlation versus causation, one of my favorite topics of all time here. Spurious predictions, survivorship bias. Basically, people are trying to fit reality to their statistics rather than their statistics to reality. And as such, it's not your uncertainty. It's not a uncertainty. It's your uncertainty. So part of this talk is to try to get you to be a little bit skeptical and a little bit suspicious when somebody just shows you the numbers. And so we'll start off with very basic. In one of my courses, I talk about what's the difference between a mean, a median, and a mode. Show of hands. How many people know what a mean is? How many people know what a median is? How many people know what a mode is? How many people realize I asked you a trick question? So say what you mean as the first place. The thing is that you can have lots of things. And this is an example. You've got a KPI that says you've got 1 hour per month trailing inside of here. Which of these would you rather report? 1.56 hours per month or 0.53 hours per month? They're both means. They are both arithmetically correct because there are lots of means. In traditional talks, we have arithmetic, which is what most of y'all thought of. Add the numbers together, divide by the number of items. That's called an arithmetic mean. You can also have a geometric mean. Multiply all the numbers together and take the nth root. And that's always in the middle. And then finally, a harmonic mean, which is take the reciprocals of the numbers, add them together, and then divide that into the number of items. And that's always your smallest number. Arithmetic means weight to the highest number. Harmonics weight to the lowest number. And so it's real simple to do that. Straightforward. Never telling a lie inside of here. So how can we lie with a mean? Well, this is a pretty good example in the US. This is 2024 data, honestly. The average income per person in the US was $59,384. There's an average of 2.63 people. Therefore, a household average should be 156,179. It's actually 109,000 and change. This is a simple way of taking two different means that actually don't apply to each other and multiplying them together or adding them together and getting a result that looks perfectly valid. This was first done in a magazine, actually two magazines, in the 1950s, trying to hype a new housing complex. And one magazine was really promoting it. And so they promoted that the household income was 5,000 and change. The other one reported it and came back and said the household income is 3,000 and change. And this is the trick they did. So it's very straightforward, very simple. And by the way, if you use this, you want $1 million, you just need to have 14.8 kids. So let's talk about deviation. And I really hate not being able to walk over and point at things here. So if someone tells you the mean temperature is whatever, 61 degrees Fahrenheit, it's actually not very meaningful. So for instance, that 61 degrees Fahrenheit is the mean temperature of Death Valley in a year. Death Valley runs a range from 15 to 104. So there's a big difference between saying that the mean is 61 and your range is 15 to 104. And so this is called basically that ranges are important anytime you look at the numbers. And so when we look at this, very straightforward, you can also look at this from the other direction. Here I can give you exactly the same samples for here, where the arithmetic mean is the exact same, but that the variance, the standard deviations, are drastically different. And so if no one gives you a range or no one gives you a deviation, they're lying to you. They are hiding something from you. It also, keep in mind that in every case in statistics, the number of samples matters. So I usually love to do this, and I'm gonna do this real quick here. Did you have coffee or tea this morning? Coffee. Coffee? Coffee? Coffee. 100% of the people at this conference drink coffee. Very simple. I didn't poll anybody. I basically asked 3 people a question and did this. Many of y'all probably have heard back again in the 50s that there was this commercial that came out that said 4 out of 5 doctors smoke Camels. You'd like to know how they got that data? They went to a conference, medical conference, and as the doctors left for the day, they handed them a pack of Camels, and they asked them what they smoked. And the ones that said, I guess I smoke Camels, got a carton of Camels. And so perfectly valid data, totally meaningless. How to lie with data. And that gets us into this sample for your desired results. Okay, so the results are only as good as your sample data. And it can be really convincing. I mean, really, really convincing here, but the size of samples matters. The bias matters. If you can't find the bias in your samples, surveys, your sample questions, look harder. It is always there. Even the people creating the survey may not realize it's there, but it is always there. So questions can be biased, interviewers can be biased. And what happens is that that bias immediately gets reflected into what we consider to be absolute truth about our numbers. We are so trusting of our numbers that we don't understand what they're actually telling us. So this is a recency bias. If you've never seen XKCD, this is one of the best ones. You got married yesterday, therefore, in 28 days, you're going to have been married another 28 times. Okay, you better order a lot of wedding cakes because your sample and your direction extrapolates to the same thing occurring. This is a recency bias, and recency basically says the most current thing is the thing that's most important. At least in my space in the DevOps world, that's not necessarily true. And when you look at this, you can have lots of different biases. You can have social desirability bias. You can have this cognitive. You can have question order bias, which is a really sneaky technique where they lead you to the conclusion that they want you to say by asking you questions in a certain order. So not only just each question, but the order of the questions can also be biased. And let's take a look at some of these. So you're trialing a new deployment tool for speed and reliability, and you survey senior engineers that were invited to try the tool. And so this is called a self-selection bias. You have selected the people that are going to give you a set of answers you want. And very honestly, I almost picked on people that were holding coffee cups because I would be a self-selection bias. And I decided it wasn't fair because somebody would call me on it halfway through this talk. So I decided I shouldn't do this. So first of all, does the survey cover the entire potential respondents category? Senior engineers, junior engineers, management, heaven only knows, HR, whatever. All these things, but make sure that the survey covers all this data because the sample survey is when they're not representative of that entire group. Very traditional, very sneaky, and shows up a lot specifically in technology questions. Okay, confirmation bias. Let me pause and catch my breath. This is my personal pet peeve. This is where they ask a question in a way that they are pre-leading the answer. And so, how happy are you? Would you agree? All these things are leading. In this case of confirmation bias can also, even though I don't use the word bias here, show up as a confirmation interpretation. So imagine, for instance, a sample survey that comes up and says, do you understand the return to office work policy? Okay. By the way, this is a real survey. I've seen the results here. And 83% of the employees said, yes, I understand the policy. You gave me the policy, I read the policy. The confirmation interpretation was 83% of the employees agree with the policy. And so this is a confirmation interpretation versus confirmation bias. It also shows up inside of that, but I don't go into interpretations. That's a totally different talk here. And so the wording of the question can skew your results. I have never, in the last 25 years that I've been really looking at this, seen a survey with no confirmation bias, ever. By the way, one of the most popular questions in this talk is how do I determine whether I have confirmation or bias or not? I'm not totally agreeing with all of the LLM tools right now, but Gemini is actually really good at reading surveys and saying that's a confirmation bias. Most of them are actually pretty good at doing that level of interpretation. And that's what, if you've got any questions, throw the question at one of the LLMs, and they'll pretty much tell you whether it's a biased question or not. They'll also point out to you where it's biased. It's kind of cool. So this one is the recency bias we talked about a little bit. So how happy are you with the tool in your most recent deployment for that? Or how beneficial has the new tool been most recently? So these are questions that are basically saying, I only want you to consider the last time you did this. So they're taking away your sample itself. You've used the tool multiple times. They just want to know the last one. And the last one may be not representative of all of the others that you've had. But they're very specifically asking just for the last one. And we are really good at following what the questions ask us to do. That recency bias can also show up if it's asked too soon after an event or too late after an event. And so recency bias provides both categories of capability. And then status quo bias. Change is scary. People don't particularly like to change things. And this one plays on that fear. So how disruptive was the new tool? How long did it take you to learn this new tool? How much effort did it take it? Is the existing process more reliable? And in most of the cases, most people would go, yeah, it took a long time to learn it. I'm so used to the other tool, I know exactly what it does. I'm not going to worry about it. And so this is a concept. There are lots of biases. We've had survivorship bias, where you only look at the data that makes it through your filters. If you're in observability space and you're filtering, you're running into survivorship bias. You may not think you are, but you are. And by the way, also, when you filter things, you're no longer being a actual, doing a sampling. You're actually doing a filter. So, straightforward. Okay. Now we get into the next fun thing. Pictures. Anybody notice any problems with this graph? There are no numbers anywhere. None. You have no idea what's going on. Okay. You have no idea how long this lasted. There's nothing to indicate anything. Picture looks really, really cool though. And in this case, this was actually looking at the approval ratings for an internal support organization over an unspecified period of time. I'll specify it as we get into it. Okay, yeah. So you need numbers, fine. Here, we have numbers, 0% to 100%. It's exactly the same graph for this. There's a really sneaky little trick that's used inside of this one, and this shows up in news reporting a lot, and they're called burnouts. Those little white spaces, you have no idea how big they are. You have no idea how much data they're hiding from you. And you have no idea what the middle section is in terms of spacing. It could be all sorts of different things. So this is a standard bias trick, burnouts for that. Okay, no burnouts. Sorry. No burnouts. Here's the line. Here's the graph. Okay, next sneaky trick. This is actually a log 10 graph. So you still have no real clue as to what's going on inside of this, but the line is now pretty straight. That's kind of cool. I could actually bias it by biasing the bottom. And by the way, you now have a scale. This was 14 months of data for here. So we now know how long it was. We actually know that it's fairly flat, but we still don't know what the numbers were. But it's up at the top, so it's got to be good, right? It's close to that 100 mark. And most people will only look at where it lives in the space for that. Okay. So this is what the graph actually looks like. This is a linear graph of the data going from, if I remember correctly, 39.83 to 40.37. Something like that. But if you remember back to what that first graph looked like, and man, it looked like it grew really fast. There is a CEO of a company who was in a board meeting and showed the quarterly results and hadn't looked at our own slides. And the graph was going along, and it did this sudden drop off. The drop off was 0.2% for that. She lost her job because it looked so bad on the graph. So it is really easy to lie with pictures. And by the way, if you really want to, you can also use a distraction technique, which is to suggest an answer. Most of you have probably looked at the red bar over there. It's big, it's great, it looks really impressive here. And what has happened is that the first bar, the second bar, and the third bar are actually doubling in size. But rather than just doubling the bars, I've actually widened the bars the same amount that I've doubled the bars. And so it looks like 1 to 4 to 16 instead. And if you really want to distract people, you put a pretty picture in there at the same point in time. Okay, now looking at the pretty picture, did anybody notice that the scale is biased itself? Yeah, so I suspect that you're at this talk, you're probably going to be checking out every single thing that I put up here on this. But nonetheless, this is a standard way. And Newsweek basically pioneered this way back in the dark ages in their magazines, and they would show these wonderful little pretty pictures, and they'd show bar, pretty picture inside of here, and everybody would immediately look at the pretty picture. Now, graphs can be lots of different things. We've seen bar graphs, we've seen line graphs. Let's talk about some of the biases that show up inside of here. And I had to go back a little bit for this one. The first one is data from 2008. And it shows, and the report was, look how poorly the Nintendo Wii is doing because so few people use it. And look how great the PlayStation is doing because so many people use it. Well, there are 50 million Wii people. This graph shows that there are about 3 million people that use it on a daily basis. Likewise, there are 30 million 360 owners. That's 3.3 million using it on a daily basis. And my print is really small here. PS3 owners at 2 million. But that's not what this graph is trying to show you. It's trying to show you that the Wii is not being very successful. Now, what this is called hiding a variable. They're showing this by saying, we are only going to take out a particular variable that we're interested in and show it to you. And it's going to give us the results we want. The second one over there is your nice standard pie charts. Pie charts, by definition, are 100%. This one is 230. And it combines 3 completely, not completely, but mostly unrelated topics for here. People who are worried about gas taxes, people are worried about road conditions, people are worried about this. It is not a pie chart, but it's representing a pie chart to show how the relative importance of each of these things are. This should have been a bar chart. This could have been done a lot of different ways. But a pie chart is a lie because you immediately assume that this is comparing all 3 things together as one possible set of answers. And so, very straightforward. We'll get into this chart a little bit more in a couple of moments. For this causation, I can do hours on causation. So if B follows A obviously caused B, right? So if you think you've got too much automation and that automation is causing problems because you've added more automated tools, it could be correlated, but it's not cause. It can be, but it's not. There is no direct link between those two on that particular category. Causation, usually stated as correlation, is not causation. This does not mean correlation is bad. This means that you cannot assign a cause to the underlying correlation. There can be confounding variables. There can be reverse causation. What you think A is causing B is actually B causing A for this. Bidirectional causations. Both things are influencing each other. You can have measurement errors. But for instance, in the middle of the summer, in Florida, shark attacks go up, okay? It has nothing to do with the fact that it's summer. It goes everything to do with the fact that there are more people in the water. And that's a confounding variable that happens. Sunburn, pretty much, sun is responsible. That's a cause. This is my favorite all-time sneaky correlation. I work this one into every single talk. This is really cool. There is almost a perfect correlation between beer sales and marriage. So, does drinking cause marriage? Or does marriage cause drinking? Neither. I could have done the same thing with house sales, car sales, anything else. This is a confounding variable, which is saying that as population increases and people become into a category where they're able to buy these things, you will get a line like this. And it is enormously interesting how often confounding variables will show up inside of that. Since we're in Oregon, UFO sightings versus patents granted in the US. Not quite a perfect correlation. This one's at an R of 9.90. The R, by the way, is called Pearson's correlation coefficient. It basically says how well something moves in relation to something else. If it was a negative number, they move in opposite directions. Positive numbers move in the same direction. The best you can have as a correlation coefficient is 0.99. There's also the coefficient of correlation, which is R squared, and the best you can have there is about 0.97-ish. So UFO sightings cause patents to happen in the US, at least the ones that are seen in Oregon. So chocolate sales or chocolate consumption versus population size leads directly to Nobel Prizes. And if you notice, Switzerland's way up there at the top, because obviously the Swiss have good chocolate, right? And the US needs to eat more chocolate because we're down here kind of in the middle lower category. Again, no correlation aspect between this. They're actually lying with two separate variables for this. One is that they're changing the rules with the population size, and they're changing the rules with chocolate consumption over the length of time of the Nobel Prizes. And so they're not equal comparisons. Okay, how many people have ever had the joy of working with Microsoft Explorer? Microsoft Explorer versus the murder rate. If you've ever had to support, and I have, Microsoft Explorer on an internal service line, you understand this one 100%. Okay, next up, find and make the data you want. There are two ways of doing this. One's called data dredging. And data dredging is looking through lots of data to find a pattern that you like. And then what's called p-hacking. P is the null hypothesis for here. Find the data that matches what you wanted to say. So this is a graph from a newspaper, a very popular newspaper, showing that global warming is not real. And it runs from 1997 to 2012, and that there was no change. We had ups, we had downs, but there was absolutely no change. And this has been touted by all of the climate change deniers that you care to think of. This is what the chart actually looks like. And they grabbed a section in the middle that was fairly recent that actually started and ended at the same point. So they've actually taken and hacked the data to prove their point, not to do anything other than that. And if you notice, the graph continues to climb and go up. So whatever way you care to interpret it, you can certainly do so. But they're basically lying to you when they're showing you only part of that data set. I tend to try to not pick on commercials, I do, or politics, but this one was too good. 82% of the country understand that it was a rigged election. This came out March 2nd, 2024. And I couldn't understand this one, so I went looking for the data. And it was hard to find, but I found it, okay? This is also known as post hoc ergo propter hoc. After this, therefore because of this. So this is finding the data that fits what you wanted to say when you wanted to say it. And this initial source was the Public Religion Research Institute. First of all, I do smell a selection bias somewhat inside of this, but nonetheless, they actually did a really good job. If you go read their report, it is spot on. They were pretty honest about what happens. And their survey size was roughly 2,500 people, reasonable survey size for these days. But in this category, they actually also broke it down by the question about the 20 election by category of what your news source was. And so if you look at the line that says most trust Fox News, and 47% and 35% basically agree with that. 47 and 35 is 82%. Wow. Now, when you start doing the math here, it comes out to that's about 54 people out of 2,500. That's all that's in that number. The number that's showing here, mostly trust Fox News, is 66. So it works out to about 54 people for that. And I can't do exactly because some of the people didn't answer this question and they didn't tell me who did and didn't answer the question. So I don't have the numbers for the specific question answers. So 54 people out of 2,508 is 2.15%. They didn't lie when they showed this. They simply picked an hypothesis and failed to tell you what part of that reasoning was. And it's very straightforward. See it all the time. If it doesn't make sense, it doesn't make sense, and it's worth taking a chance to looking into it a little farther. Okay. So statistics are actually a really simple way to mislead. People trust numbers. People believe the numbers that are told to us, and we are pretty much, in a sense, trained in our education processes to believe the results and analysis that come out. I usually start up asking if anybody's a data scientist in the room, because if they are, I apologize to them up front, because they are incredibly good at finding the answer you want to find for that. And no matter what, look for bias. Always look for bias. If you don't remember anything else from me standing up here for 40 minutes now, look for bias. That's really important. Data dredging. People will find the data that matches their source for that. Unclear, incomplete. They're not showing you a range. They're not showing you a standard deviation. They're hiding something from you. When it comes to correlation, always keep in mind the things that could be affecting your correlations, and that correlation is not causation, but correlation can be just as important. And my favorite example of that is also sort of in the DevOps category here. You have just pushed a new release of a product, just pushed a new release of a microservices code, and something goes wrong. So is the push correlation or causation? And you can argue either way, or I can. I need 2 beers, but I can argue that either way here. And keep in mind that pretty pictures are used as distractions in all cases. And finally, keep in mind that 90% of every error is caused by somebody who's right-handed. So with that, let me say thanks for listening to me. You can find me online in lots of places. If you notice, I had these little pithy quotes down underneath this is mine. Statistics are history. History is written by the winners. So never trust the statistics unless you actually know the history behind them. So with that, thanks for listening to me. And if you feel like following up a little bit more, some suggested reading, my slides are available on GitHub, but for some suggested reading, How to Lie with Statistics by Darrell Huff is the ultimate source for any way to lie with statistics. It was written in 1957. It is still valid today, and you will laugh your entire way through the book. So just keep in mind that you can also use the other way. I was a soccer ref for 10 years, and Chris Wood can become Nottingham's all-time leading scorer, just as long as he scores 93 goals this weekend. So with that, thanks for listening to me, and if there are questions, I'll be glad to try to answer them. And this is absolutely normal, dead silence. Yes?
I just wanted to second the recommendation for calibiggen.com. That is a really fun website. Just go there, or just Google spurious correlations and take you there. And it's so much fun to spread.
Yeah. Yeah, thanks for calling out. Tyler Vegan. Tyler started doing this work. He also is now taking, in certain cases where he's got these wild correlations, he has massive data sets. He just throws them in a computer and has Pearson's coefficient run against them. And if something shows up, he makes a chart out of it. He's now taking those charts, handing them off to LLMs and saying, justify this as a causation. And it's hilarious what comes out of those things here. Also, if you notice, my shirt says your opinion is not statistically valid. This is also something, if you're interested, a history of the Bayes theorem. Your opinion is absolutely valid as long as you're a Bayesian. And by the way, there are two types of statisticians in the world. They're determinists and they're Bayesians. I am a Bayesian. I will change my opinion on new information every time it comes in. Determinists say, oh, look, 90% of the time it's supposed to be this, therefore it must be that. The perfect Bayesian example, by the way, was The Price is Right with Monty Hall. And Monty Hall had 3 doors. Behind 2 of the doors were goats. Behind one of the doors was a brand new car. And he'd say, pick a door. And somebody say, I picked door number 1. And he goes, okay, open door number 2. And behind door number 2 would be a goat. Okay, and then he would look at him and say, I'm going to give you a chance to change your pick. Okay, so how many people think it doesn't matter? Changing your pick doesn't matter. How many people think it does matter? How many people think that it's crazy to do this and no matter what, it just isn't going to happen? Well, it turns out that, first of all, Monty Hall can talk you out of anything. There was a newspaper reporter who went there and was understanding this, and Monty Hall talked him out of the right answer every single time. Statistically speaking, it's better to change your answer because you've got 3 doors, 1/3 probability each door. You pick one. That's still 1/3. You've now picked that door. It's 1/3. You have 2 doors left. That's 2/3. Takes 1 door away. The 2/3 doesn't change. It just moves to the final door. And so it's always fascinating when you look at this. Bayes' theorem was discovered in the 1700s and promptly everybody complained about it. Nobody believed it and so forth. And then was rediscovered roughly 60 some years later, and nobody believed it, and it is still today argued about. There was actual fistfights at the American Statistics Association in the 50s over Bayes' theorem. But Bayes' theorem, by the way, is the reason they broke the Enigma code. It's how they got people back from the moon in Apollo 13. So Bayes' theorem may be really statistically confusing, but by the way, just works. And so that's why people live with Bayes' theorem. Every time a piece of information comes in on your bug report and you've changed, that's a Bayes' theorem. So sorry, that's part of the other talk I do. So cool. With that, yes.
Just a brief anecdote that I wanted to share. I once was trying to tell someone about the Monty Hall problem, and their response was, "But I wanted the goat." That's
actually a really good one. Yeah, they tried doing Monty Hall in Germany. I can't pronounce it, but their Prius is something for this, and it never caught on because they never understood why, to your point, somebody wouldn't just take the goat. So with that, we have 2 minutes left. Anything else? Oh, geez, yes.
The lead slide,
I'm sorry.
the video game console slide, what was the, I missed what you called it, and make it like just the sampling with the percentages and everything?
I'm sorry.
The Wii slide, video game slide with the Wii and the PlayStation.
Oh, that one? Yeah. Let's go back to this one. This was a. Sorry, I'm going to move away from the microphone. This is a variable removal category. So what it is while it's looking at percentage of users, it's not telling you the number of users. So the user categories are artificially defined by showing this has the most users, but the lowest percentage of users. So it's the same category. That one over there, pie are round, I guess. So cool. With that, thank you, and I will turn you loose for the rest of your conference day and hope to see you tonight at the event.